It is my pleasure to introduce Professor Stefano Forte. Stefano, University of Milano Statale, is a full professor at the University of Milano Statale. He will talk about machine learning, the structure of the proton.
Okay, so thank you very much. Thanks for this nice introduction. Actually, Alessandro asked me to give a kind of general introduction to parton distributions, which means actually QCD factorization. So what I'm going to do in my lectures today and tomorrow, actually, Alessandro also asked me to use the blackboard. So what I'm going to do today and tomorrow is discuss some very basic things. Today I'm going to cover essentially factorization in deep inelastic scattering, which I'm sure everybody here knows and has heard about many times. I try maybe to focus on things that are sometimes not so clear, or that people might be slightly confused about or emphasize things, but I'm sure it's stuff that many of you will have heard already. I'm going to ask actually in a second about your background. And tomorrow I'm going to focus more on actually determining PDFs, what you do. But again, from a fairly theoretical point of view, so still using the blackboard. And then starting tomorrow afternoon, and then on Thursday, there will be a couple tutorials. We've been doing this already with Tommaso Gianni, who was my master's student long ago, and he's now a postdoc. And he's I'm gonna be there actually during the first tutorial tomorrow, and he's gonna show you how to actually write a piece of code in such a way that at the end of the 4 hours of tutorial, you can actually do a fit of a parton distribution to real data using a neural network methodology. So that, we start from very basic formal stuff, and at the end, if everything works, hopefully, you should be able to get to the point of actually doing something which is fairly close to what we do when actually working out frontier developments of parton distributions. So before I start, however, I'd like to, Alessandro gave me some feeling of that, but still I'd like to ask, how many of you are experimentalists? Could you please raise your hand? And, just cross-check theorists. Okay, so it's about half and half, maybe a slight dominance of theorists. And the other question, the other way of dividing you is how many of you would identify themselves as nuclear physicists? No one, very good. So everybody else, actually, how would you identify yourself, as a particle physicist or a hadronic physicist? Okay, so everybody's nodding. Maybe not everybody, but almost everybody. Okay, so fine. That's that's good to know, because then I'm sure that you all had a background on QFT and renormalization, Feynman diagrams, standard model, QCD. So you probably know everything which I'm going to talk about, but I'll try to stress things that sometimes are not so obvious. So what I'd like to do today is start. I'm going to introduce QCD factorization. I could do this by looking at the LHC. I'd rather do it looking at deep inelastic scattering, first of all, because it's easier. There is a deeper conceptual reason, which is that DIS is the context in which one can actually prove rigorously QCD factorization using the Wilson expansion, the operator product expansion. And that helps in understanding what's going on when then one goes to hadronic processes like at the LHC. And also, after all, the electron-ion collider is going to start in less than 10 years, hopefully, which means that a lot of recent developments have been happening in the theory of deep inelastic scattering. For example, say, next-to-next leading order corrections to semi-inclusive DIS were computed for the first time a year ago. The PAWEG Monte Carlo was extended to DIS within the last year, and so there is a sense in which DIS, which was a little bit forgotten after the demise of HERA, the electron-proton collider in Germany in the early 2000s, is becoming fashionable and interesting again. But at the end of the day, the main motivation is really theoretical. So, DIS, you all know about, we are talking about. So one thing I'm going to try and do in the sequel of these lectures is try and skip on irrelevant technical details. So, make things easier. So, for example, now that I'm going to describe DIS, I'm going to say electron-proton scattering with the exchange of a virtual photon, which is not quite true. It could be a neutrino, you could be exchanging a W or a Z, but this is inessential for what I'm going to talk about. And there are many more simplifications that I'm going to do in the sequel of this kind. Like Alessandro said, please feel free to stop me at any time. If there is something that I didn't explain clearly, or you didn't understand, or you'd like to know more about, don't hesitate, stop me. I'd much rather skip some topics than lose your interest or attention. I always say, probably you've heard this already, but there are no stupid questions, there are only stupid answers. If you hesitate because you think maybe I should have understood this, chances are that if you ask the question, half the people in the room will be grateful to you because they were having the same question. So don't hesitate to ask questions. Okay, so we are looking at the scattering of a lepton, which we call conventionally electron that exchanges a virtual photon that, like I said, could be a W or a Z on a proton. So the kinematics is quite easy, and it's described by a momentum Q, which is the momentum exchanged by the incoming outgoing lepton. And in actual fact, the electromagnetic part of the process is not so important. So effectively what we are looking at is the scattering of a virtual photon with momentum Q over a proton with momentum P that produces a generic final state X, which is in general a bunch of stuff, which could be hadrons, but will be actually quarks and gluons and perturbative QCD. So the whole kinematics is basically described by two momenta, P and Q. Now, P square is the proton mass, which we are going to neglect because we think that we are looking at a high energy process in which the mass of the proton is not relevant. And then at this point, we have one single dimensional quantity, which is the virtuality of the photon, which I call minus Q square, so that Q square is greater or equal than 0, because it's easy to show. I could do it for you, but I'm sure you know it, that this 4-vector Q square here has a negative modulus, so that big Q square instead is positive semi-definite, and then P square vanishes, Q square is the only dimensional variable which we got, and then of course we also have P plus Q square, which is the invariant mass of the final state, which I called X over there, which is usually called W square. By the way, in deep inelastic scattering, there is a whole lot of terminology that has been accumulating over the years. I will use some of it, but maybe not all of it. And of course, this is then easy to work out in terms of, so this is just minus Q square plus 2 P dot Q, and it's actually convenient to define, the whole kinematics. So, the whole kinematics is described by this guy, and it's useful to keep Q square as the only dimensional variable, and then define a dimensionless ratio, which, as you all know, is the Bjerkén variable X, which is defined as Q square divided by 2 P dot Q. Okay, so the whole kinematic is encoded in the dimensionless ratio and one dimensional variable. And please note that, of course, many of you will have in the back of their minds that this has something to do with proton momentum fraction or something, but this is really an experimental variable. I mean, this is something that you measure in experiment. It's something that you get by measuring the invariant mass of the final state and the virtuality of the photon, which you get by measuring the electron kinematics. So this is it's something that you can actually extract in an experiment. Okay. Now with the kinematics which I wrote up here, yeah, sorry. Let's say that for the time being, this is a pure, like I said, the whole kinematics is described by, three vectors, one of which is light-like, and two of which is the proton mass, and the other two I've written here, and so for the time being, this is just a way of parameterizing the kinematics, and then in the sequel, we are going to try and understand how to relate this to something that we can actually calculate in perturbative QCD. Okay, but I want to stress that this is really now defined as something that you can measure, and then whether or not it is related to, say, the proton momentum fraction is something that we are going to discover, and that comes in a relatively indirect way. Okay. Very good. So, okay. So, having written the kinematics like this, it's easy to see that this, in fact, is q squared 2p dot q is obviously the what I've been calling here w square. Minus q square minus the proton mass. So this is minus m square minus little q square, but this guy I'm neglecting, and this is actually minus big Q square. So this is just q square divided by m square plus big Q square, okay? And sorry, plus. And this immediately tells me that w square is written as q squared times 1 minus x over x, which I get by just inverting this relation. And, I call it xbj here to emphasize that this is the experimentally measured variable. I'm going to just call it x from the time from now on and drop the bj, but it's the same x which I've used over there. Okay, so this is all the kinematics that you had that you have to remember. I'm sorry. Once I've defined this in this way, you immediately see that x must be between 0 and 1 because the invariant mass of the final state is between 0 and infinity. Obviously, if you pump more and more energy into your system. Very good. So at this point, let's say I want to compute this by computing Feynman diagrams, and if I do this, the amplitude. So I said I'm going to neglect the electromagnetic part, so the top part of the diagram. But let's say I write it for 1, and then I drop it. So if I just want to write the Feynman diagrams for this guy here, like we've learned in the introductory QFT course, I write it as some square electric charge. Again, I'm assuming I'm exchanging a photon. It would be a weak charge if I was exchanging a W or Z times Dirac spinors related to the incoming and the outgoing electron. So it's U bar K prime, gamma mu U of K, a propagator for the photon, which is 1 over Q square, and then a sum over all possible final state X of the matrix element of an electromagnetic current, J mu, between the initial state proton P and all the possible final states X. Okay, and when I write the cross section is going to be the square modulus of this guy here with a phase space factor. So my cross section d sigma is going to be something that looks like well, I have a phase space which is related to the outgoing electrons, so there is something like 3d3k prime divided by twice the energy of the outgoing electron times e to the 4th times q square, which is the square of this guy, and then I have the modulus square of this whole thing, which I can write as some leptonic tensor L mu nu times a hadronic tensor W mu nu. Now, the leptonic part, which I'm going to write once and for all, and it's going to disappear from now on, is the usual thing that you get when you take the square modulus. You sum over initial polarizations. Sorry, you sum over final polarizations. You average over initial polarizations. So you end up getting the usual Dirac trace, which is kind of easy and simple, k slash prime, gamma mu, k slash gamma nu. And the hadronic tensor, which we are going to focus on, is the interesting part, and is actually the sum over all final state x of the matrix element of J mu, well, dagger x, x, J nu p, right? So it's the square modulus of this guy here summed over all final states, which you can actually write using the optical theorem as twice the imaginary part of the forward amplitude, so the matrix element between P and P of the time-ordered product of two currents J mu, J nu. Okay, so sometimes people are confused and say, hey, wait, why is there an imaginary part? Surely this is a sum over all states, so it's a completeness relation and I can drop it. Well, hang on. I mean, as you see here, I'm actually writing a cross-section which has a phase space. So here I'm not summing over all final states. I'm having actually a phase space integral. The phase space integral has a momentum conservation delta function between the initial momentum and the final momentum. And what the imaginary part does is precisely extract from the sum over all possible intermediate states only the ones that are on shell, meaning only the ones for which the momentum transfer from the initial state and the intermediate state is such as to conserve the form momentum. So this is why you need the optical theorem and the imaginary part over there. So, you know, schematically, what I've been doing when writing this last step here is to take a sum over all final state of the square modulus of the Feynman diagram, which I've drawn up there, you know, the one with P, Q, and X. I took the square modulus of this, and this has been written as a sum over all states where I get this, this, then this, and this. I'm taking the square modulus, so I'm multiplying by its complex conjugate, and I'm putting on shell all the intermediate states here, which is what I'm doing when taking the imaginary part. And the factor of 2 is because I'm looking at the imaginary part as the difference between, the complex, the complex part of the log above and below the cut when all the intermediate propagators go on shell. Yes. Say that again, sorry? No, here X is, I'm sorry for the mix-up. Here, this is a big X, which means all intermediate states. So this is a sum over all intermediate states, nothing to do with X Bjerkane. Oh, at this point, I'm just looking at the I'm just saying the W square here, yeah. Okay, so this is just like saying the W square is between 0 and infinity. Okay, so this guy here, so when X goes to 1, this goes to 0, and when X goes to when X goes to 0, this goes to infinity. So I'm just saying that this is positive. Okay. So the final state mass is the total energy that you're putting in. It's the total center of mass energy of the virtual photon-proton collision. Okay. It can go up to infinity if you have, if you're ramping up the energy of your collider to infinity. And then, the fact that this is less than 1 simply means that this is positive. And the fact that it goes all the way to 0 means that in principle you can go to infinity. So I'm just saying that the center of mass energy of the final state is between 0 and infinity. Okay. Very good. Okay, so yeah, so this is then twice the imaginary part of this. Okay, so I have to introduce a little more boring technology, which I'm going to forget about, which is parameterize the hadronic tensor. Now, the hadronic tensor is the most general tensor that you can construct out of the two vectors that we got, p mu and q nu, with a constraint that it's conserved because of current conservation here. So this is a function of p and q that must satisfy w mu nu, q nu, W mu nu Q mu equals 0, right? And this means that we can actually write it quite in general as Q mu Q nu. I pull out a factor of Q squared just so that this is, well, for, let's say, for later convenient, plus dot dot dot, where what I'm putting here after dot dot dot, I'm going to skip right now, but it's you know, the terms that you build out of P and Q in order to ensure that this is going to be orthogonal, so something that contains G mu nu with some coefficient, which is called F1 of X and Q square. So this is a tensor, so I have to construct it out of the two vectors. The coefficient is a function which I decide to write in terms of my Lorentz invariants, which are one dimensionful one, which is q squared, and one dimensionless ratio, which is what I called x Birkin, right? And a bit which instead is p mu, again, plus dot dot dot, where again, the tensor structure here is determined by the condition of momentum conservation for reasons that have to do mostly with history. There is also a factor of 2x divided by q square here. I mean, Q square I want because I want this to be dimensionless in the same way that this factor was dimensionless. The factor 2x is historically motivated, and the coefficient of this guy is called F2. Okay, so you know the thing to remember is that I basically have two tensor structure, Q mu Q nu and P mu P nu. Obviously, sorry, I didn't say that, but it should be obvious. The tensor W mu nu is a symmetric tensor because of the way it's been constructed. So either Q mu Q nu or P mu P nu, and the rest determined by conservation, and the two coefficients which I'm writing down here, which turn out to be dimensionless if I define things correctly, are called structure functions, as you probably know. But you know, again, the thing is the two structure function F1 and F2 are there because I have two vectors, and I can do two symmetric combinations of this product of two vectors. This is for parity conserving interactions. If I turn on the weak interaction and then I have W and Z exchange, I would have an extra term, which I can construct after out of parity violating terms. But again, this is really inessential for what I'm going to do in the sequel. So let's stick with the two structure function. As a matter of fact, I'm going to focus on one of the two structure functions in the sequel. Okay, so obviously what we are interested in is computing this hadronic tensor, and what I'd like to show you today is QCD factorization, which you all know and love. And the way this is derived in a completely formal and rigorous way is using the Wilson expansion, the OPE. So the idea of the Wilson expansion is that we now, so we have used the optical theorem. Having used the optical theorem, we reduced, I'm sorry, it had disappeared. We reduced our problem to evaluating the time-ordered product of two currents in the proton and then taking the imaginary part, which we're going to do later on. So we really want to evaluate this guy here, and this is done by using the OPE. So maybe I can leave the kinematics on for a while and stick to this blackboard here. Yes? So Q mu, Q nu, P mu, P nu. Yes? Yeah, so this is contracted. I'm just saying that if I contract Q either to with the first or the second index, I get 0. Okay? And this then determines this to be minus G mu nu, this to be minus P dot Q, etc. Okay, so far I did DIS. Now, OP, which is gonna lead us to factorization in a second. So, little reminder of field theory that you probably all know about. The idea of the operator product expansion is that if you have two currents which are localized in 2 points in space-time, which I'm calling 0 and z, I mean, it could be x and y, but I might as well choose one of them in the origin, in the limit in which z goes to 0, so the separation of the two currents is small, can be written as a sum of local operators, OK, evaluated in one of the 2 points, times coefficients ck that depend on the separation. And the idea is that these are local operators. And these are actually C number coefficients. Okay, so you can factor the space dependence in C number coefficients. And, in order to understand, I mean, of course, at the end of the day, we want to connect to Feynman diagrams. So we want to look at this guy in momentum space, and we want to take the matrix element, because at the end of the day, we want to evaluate the imaginary part over there. So in momentum space, what we'll be looking at is something like an integral d4z exponential of I q z of a matrix element in the proton of the product jz j0 p. And this, if I then use the OPE, is a sum over K. So K is what? Well, it's a complete operator basis. So you have to introduce here all the possible operators that are allowed by the quantum numbers of this guy here. So if this carries, I don't know, baryon number 2, then you'll have all the baryon number 2 operators on the right-hand side. You conserve energy, momentum, but other than that, you have a complete basis of operators. So here there is a sum over K. Remember, the CKs of Z are C numbers, so they come out of the matrix element, and then you have matrix element P, OK, P, sorry, I wrote of Z, but this is wrong because I Fourier transformed with respect to Z. So they are functions of Q, actually. And you see that once I go to momentum space, this is quite nice because all the dependence, all the non-trivial dependence on the momentum transfer Q is in the C number coefficients, while these matrix elements here only depend on the momentum P because they are proton matrix elements, and the only momentum which is known to the proton is P. Right? Okay, so these guys are only a function of P, and of course, so these are only a function of P, and once we write everything in terms of Lorentz invariant quantities, P squared is equal to 0. So these guys here are just are going to be just coefficients. So the reason why the OPE is interesting is twofold. I mean, first of all, because it factorizes the dependence on Q from the dependence on P, and this is what's going to lead us to QCD factorization. But it's also very useful because it allows us to classify the operators on the right-hand side based on their dimension. This because by pure dimensional analysis, the coefficients CK of Z must be proportional to Z modulus, because we extracted all the tensor structures. At the end of the day, we are going to write an OP for these guys here that are scalar. So all the vectors have been pulled out, and therefore these coefficients will only depend on the Lorentz invariant quantity, which in position space would be a modulus of Z, and in momentum space is a modulus of Q. And then by dimensional analysis, they must scale in such a way that the dimension of the coefficient times the dimension of the operator is equal to the dimension of the left-hand side. Okay, so if I say that the dimension of my operators G in powers of momentum is m to some dimension which I call dj, and let's say I have the same current twice, like in the hadronic case, this by m here I mean mass dimension as opposed to position dimension. So z here must be minus twice dj, because this guy must have the same dimension of this guy, and then I have to subtract the dimension of the operator, so minus dk, which is the dimension of the operator, okay, which means in terms of q dimensions that this goes like 2dj minus dk, where dk is the dimension of the kth operator. And this is why the expansion is useful, because you see that this tells you that when q goes to infinity or z goes to 0, so z goes to 0, which is the same as q going to infinity, so our q square is going to infinity, it's the operators with lower dimension that are going to dominate, because the ones where dk is very big are going to be suppressed by high powers of d. And you know, we are going to see this explicitly in a second, but you can imagine immediately that we can make the momentum dimension of operators as big as we want. We just add more derivatives, right? So the dimension is bounded from below, but not from above. And this means that there's a small number of operators that are going to dominate, the ones with lower dimension, while all the high dimension operator will just decouple in the limit in which the separation is going to 0. There is, however, a little complication that I'm sure you have heard about, but I'm going to go through now in a second, which is that this kind of naive argument actually only really works in Euclidean space. So this is Euclidean scaling, which I've shown here. We are actually working in Minkowski space. And in Minkowski space, we have the complication that it's obviously possible to have x square, or say z modulus, that goes to 0, but the single component of z actually remain different from 0, right? Because you can have a light-like vector where the components, the individual components are non-zero, but the modulus of the vector is going to 0. In moment, so this z going to 0, let's say, does not imply that z mu is going to 0. And in momentum space, this means that q square going to infinity does not imply that p dot q divided by q square goes to 0. And in fact, you know, this is quite important. You know, if we were in Euclidean space, of course, you'd say, well, q square goes to infinity. Here I have q linear. Here I have q square, and therefore this must be going to 0. But in Minkowski space, this is not necessarily the case. So we can take the q square going to infinity limit with fixed Bjerkane variable. I thought I'd written all the kinematics here, but I dropped the Bjerkane variable. Let me put it back. So this means that the fact that q square is going to 0 does not necessarily mean that the Bjerkane variable is going to 0. We can keep it fixed. And this makes the power counting a little more complicated. Again, as I'm sure many of you know. In fact, I'm going to ask you in a second. So let's do now Minkowski scaling. So in Minkowski space, because of this fact, I can introduce operators with vector or tensor indices. And then if I have an operator like, so if I have a contribution to the OPE that goes like, say, C and K of Z times Z mu 1, Z mu K. So the index here, K, counts how many Z's I have, times O, N mu 1 mu K. Okay, so this is scalar. However, the operator now is a tensor operator, which contains at most spin k, right? Because an object with k vector index, you know, yes. The n counts the operator, so the n is going to count the dimension of the operator. Now I'm going to write dn. So give me 1 second, I write one more equation, and then you can ask the question again. So I'm going to write a modified version of this, where now I write that ck of z is proportional to z modulus at the minus 2dj minus d. Sorry. Yes, you were right to ask because I've been stupid. I exchanged two indices. Sorry. So I want to call the indices mu1, mu n. This is mu1, mu n. This was k. And this is now dk minus n. Sorry, I had interchanged k and n, and this is why you were confused. Okay, so now I'm having still k as the dimension of the operator. But now, because I also have these powers of z, the coefficient ck scales with the dimension it had before, but now I have to subtract the dimension which is carried by all the z prefactors, which are contracted over the indices of the operator. And this means that if I simultaneously increase the dimension of the operator, but also the number of tensor indices, this guy can stay fixed, and therefore I get an infinite tower of operators that all have the same scaling, that have different number of free tensor indices. Therefore, they have different maximum value of the angular momentum that they carry, and also different dimension, but they all have a fixed dk minus n, and then this leads to the same scaling. Okay, so if I take all the operators for which dk minus n is fixed, and you see, if I add an extra z, then the dimension of the operator goes up by 1 unit because I'm compensating for the dimension of this guy, but also the number of indices of the operator goes up by 1 unit. So if I add more and more z's, the thing is kept fixed, and this is called twist. And it's, sometimes referred to as dimension minus spin. It's not really dimension minus spin. It's really dimension minus the rank of the operator, which is the maximum spin that the operator can carry if you symmetrize all the indices of the operator itself. Okay, so in momentum space, yes. No, we didn't go from Euclidean space. We are always in Minkowski space because we are doing a field theory in Minkowski space. I told you how the coefficients of the operator would scale if we were in Euclidean space. Because in Euclidean space, we can make the simple assumption that each of the components of the 4 vector scales like the modulus of the 4 vector, because the modulus is just the sum of the squares, right? While in Minkowski space, we can't because we are taking the difference. And therefore, the fact that the square modulus is going to 0 or to infinity in momentum space does not tell us what the single component of the vector are doing. Okay, so first I did the easier version where I derived the scaling based on the naive assumption that each of the components of the vector scales like the square modulus of vector. And then I realized that this was not correct. And in Minkowski space, I have to do this slightly more difficult thing. Okay, so while I just finished the sentence. So the upshot of all this is that while in Euclidean space, there is a finite number of operators that contributes to the OPE in the limit of z going to 0 or q squared going to infinity. In the Minkowski space, I always have an infinite tower of operators that give the leading contribution to the OPE, which are those that have the lowest value of the dimension minus spin, so the lowest twist. And you can see, so before, I said, the dimension is bounded from below. I have lower dimension operators, and I cannot go make them lower dimension, and all the high dimension ones disappear. While here, obviously, I have an infinity because I can always add an extra derivative, but then if I add an extra d mu, I get both an extra derivative and extra index. So I increase both the dimension and the spin, and therefore I have an infinite tower of operators, which I'm going to write in a second, which all have the same minimum twist. So I switch from a situation in which I have a finite number of operators giving the leading contribution to a situation in which I always have an infinite tower of operators giving the dominant contribution. Question? That's a very good, that's a difficult question. In general, no. So typically they are the same at leading order. So we are going to get to the computation of Wilson coefficients in a second, but you know, by and large, the way things work is that the way we compute Wilson coefficients is by exploiting the fact that the Wilson expansion is universal. It's a property of the operator. So you know, we are interested in evaluating a proton matrix element, but we might as well evaluate a matrix element in a simple state in which we can calculate. Okay, so at the end of the day, we are going to calculate Feynman diagrams. So then your question comes down to the question, is a Feynman diagram computation in Minkowski space and Euclidean space giving the same answer? And as you probably know, the general answer is at tree level, yes, but as soon as you do a loop calculation, no, because you have a non-trivial analytic continuation of you know, the four momentum integrals that correspond to loops, and therefore, in general, the coefficient, the leading order coefficient functions which you compute from tree level diagrams would be the same, but the beyond leading order they want. Yeah, that's a very good question. More questions? Okay, very good. Right, so yeah, I think I'm gonna get where I wanted to before the break. So yeah, my plan is to keep going for 10 more minutes or so and then have a 5-10 minute break, because we must stop at 1 sharp, otherwise you'd skip lunch, which you don't want to do, you'd kill me, and I want to survive. Okay, very good. So we got our Minkowski scaling, we wanna go to momentum space, obviously, which is what we're interested in. So we wanna take the Fourier transform of what we get when we will plug the product of C, N, K, Z, mu, mu, O, mu in our OPE. So what we really want to do is compute something like an integral d4z exponential iqz, and then the proton matrix element of the guy which I've written up there, which is C, N, K of Z, Z, mu 1, mu n, sorry, I'm screwing up. This was mu k, right? Because, no, I have to be careful. What am I calling n and what am I calling k? I'm calling k the dimension of the operator, so this is dk, and I'm calling n the number or the twist or the spin, sorry, the spin of the operator. Okay, so this is, well, CNK, fine, it carries 2 indices. Then I have n indices here, and then I have my operator OK, mu 1, mu n. Okay, and then I have the proton matrix element. Very good. Okay. So the coefficients are now a function C n k of modulus of the momentum variable, which is conjugate to z, which is q, and that's q square, which I decided to trade with big Q square. So the coefficients depend on big Q square. Okay. Then I have the Fourier transform of these guys. These guys have the dimension. So the Fourier transform of z is q. So I have to replace this guy by q. This has a positive dimension in unit of length. So dimension minus 1 in units of momentum. So this is like q mu divided by q square. Okay, because like this, it has the same dimension, and I have as many of these as I had z's. Okay, and then I have the matrix element of OK mu 1 mu n in the proton state. And remember from the OPE that this guy here can only depend on this guy here. The matrix element can only depend on P. So this guy will have tensor indices that can only be carried by powers of the P square momentum. So what I'm going to do is write P O K mu 1 mu n P as P mu 1 P mu n. In fact, for reasons of convenience, which will be immediately obvious, I also pull out a factor 2 for each p, which I can always do because it's just a definition of a normalization, times something which I call a k n, which now is only a function of p squared, so it's a function of 0. It's just a number, if you wish. And this is usually called reduced matrix element. Okay? And you immediately see that if I substitute this expression up here, I get that my Fourier transform here is just a bunch of, so Cnk of q square times 2p dot q divided by q square, because you see each of these two p's gets dotted into a q to the power n times a n k, and I'm not going to write p squared because that's just 0. Okay, and you see this is the right-hand side of my OPE, which I had on the left-hand side. So at the end of the day, what this guy is going to be is the proton matrix element of the product of the two currents once I properly identify the various contributions, which I'm going to do in a second. But for the time being, what I'd like to point out to you is that because of the way I set up the whole formalism, so these guys are all dimensionless. They are all powers of X Birkane, right? So these are dimensionless. And the coefficients C and K of Q square and A and K, they all have the same scaling, right? Because I've chosen them, so same scaling if the twist, so dk, if twist dk minus n fixed. So in the limit of large Q square, I'm going to look at the leading twist contribution, which is all the operators that have the lowest value of dk minus n. I include all of them, and then I get that I have an infinite sum of contributions that looks like this, where all the contributions scale in exactly the same way, which is the way which I wrote up there. This I wrote in terms of z, and the scaling in terms of q square I can write here. So ckn scales q square like square root of q square, which is like z here, to the power 2 dj minus dk minus n. So you see that the lowest twist operators in the limit in which q squared goes to infinity are the one that dominate, because if twist goes up, then you get a higher suppression. Okay, so at this point, we need to know what are the lowest twist operators. Give me 5 more minutes. No, actually, maybe not. Actually, okay. So maybe this is a good time to have a break. We can have a break here. It's 12 noon sharp, and yeah, that's fine, because this is okay. So this concludes my discussion, my kind of general formal discussion of the OPE. After the break, I'm going to show you the OPE for the AS, which is what I was trying to construct. Questions? Yes. They have the same scaling behavior if I keep the twist fixed. Because you see, the scaling behavior is given by the dimension of the operators on the left-hand side, which I must reproduce, and then the dimension of the operator minus the number of vector indices of the operator. So if I increase the dimension, but also increase the number of vector indices, they all have fixed scaling. Okay? So very crudely speaking, up to the dj, the scaling is, the modulus of q square raised to minus the twist. Okay, so higher twist goes away, low twist dominates, and you just get square root of q square raised to twist, to to minus twist. Yes, there's a question? Uh, Yes, you're right. So yes, yes, yeah, absolutely. So I'm being a bit sloppy here. Yes, yeah, yeah. Of course, if you want to be careful, you have the dimension of the measure here, and but then you know, I'm being sloppy in many ways. If you are down to that level of precision, you will notice that I actually use the same notation for the C's of, you know, Cn, I wrote Cnk of z and Cnk of q squared. Now, this is obviously a complete abuse of notation because one is the Fourier transform of the others. And then you, I mean, the idea is that I set up things in such a way that the missing coefficients are reabsorbed in the redefinition of the operators. Yeah. But so yeah, yeah. So I mean, I insist. You know, I'm glossing over many technical details. What I'm going to do in the end is assume that I define things in such a way that all these guys here are dimensionless, and here I'm looking at the dimensionless expression. Now, of course, in order for this to be dimensionless, I have to make sure that I I normalize properly my operator basis in the beginning in such a way that then when I do the Fourier transform, I write the correct expression. On the other hand, this is actually easier than it sounds because in actual fact, all the, so, you know, the reason why I started from position space is mostly for pedagogical reasons, right? To explain things, I'm going short distance and I want to emphasize the fact that short distance is the same as the reciprocal of, you know, infinite energy and so on. In actual fact, obviously, Feynman diagrams are something that you calculate in momentum space. At the end of the day, everything is done in momentum space. The structure functions will be defined as a function of x and q squared, but x and q squared are also momentum space quantities. So the position space here is something you can forget about. At the end of the day, everything will be defined in momentum space, and then you define the structure functions in such a way that the structure functions are dimensionless, and then you write an OPE, which we are going to do in a few minutes after the break. We write an OPE for the structure function. So I'm afraid I erased the definition of the structure function, but if you remember, the definition of the structure function, you know, had these prefactors of p mu, p nu. Those are all inserted in such a way that the structure function is dimensionless. And then it's easy to keep track of things because we are going to write an OPE for a dimensionless structure function, which is going to be written in terms of dimensionless reduced matrix elements and dimensionless Wilson coefficients. And you just have to make sure that when you compute the Feynman diagrams, all the dimensions. So actually, the dimensional dependence is the easiest thing. To be frank, the most difficult thing is the factors of 2 and pi, which you have to keep right when you normalize the operators. But the dimension you match by trivial dimensional analysis. Thanks. More questions? Yeah, 12:10 is difficult because it's already 5 past 12. Let's do 12:15, but let's say I really start at 12:15, so try and come back at 12:13 so I can start at